Our last lesson in the module on counting will be a little bit more about binomial coefficients and the binomial theorem. The binomial theorem gives us a formula for expanding a binomial like x plus y raised to some power n, where n is a non-negative integer. The coefficients in this expansion, it turns out, are precisely the binomial coefficients that we've been using to count combinations, which is why we called them binomial coefficients. So using our basic algebra skills, we can find the first few expansions. X plus y to the 0 is going to be 1. X plus y to the power 1, of course, is x plus y. If we have x plus y squared, we know how to do the distribution. X plus y times x plus y. We'll do first x times x, and then x times y, and then y times x, which I'm also going to write as x times y because it doesn't matter in which order we multiply them, and then y times y, which is y squared. So we know that from high school, and you can combine these like terms, and you can write that as x squared plus 2xy plus y squared. If we had x plus y cubed, then we can continue this process, and you'll get something that looks like x cubed plus 3x squared y plus 3xy squared plus y cubed. And if we had x plus y to the power 4, it looks like this, x plus y to the power 5 looks like this, and so on. So if we take a look, for example, at this expansion for x plus y, everything to the power 5, you might notice that the coefficient of the third term is 10. That's equal to 5 choose 3. The coefficient of the second term is equal to 5 choose 2. Rather, I'm sorry. The coefficient of this should say the fourth term. So that's this coefficient is 5 choose 3. And the coefficient of the sixth and final term is 5 choose 5, which is 1. So if we rewrote this expansion, we could write it as 5 choose 0 times x to the power 5, which is 1 times x to the power 5, plus 5 choose 1 times x to the power 4 times y, which is 5 times x to the power 4 times y. And then the third term, 5 choose 2 times x cubed times y squared, 5 choose 3 times x squared times y cubed, 5 choose 4, and 5 choose 5 is also 1. So in summary, the first term in an expansion of the form x plus y to the power n, the first term will be simply x to the n, just like we had here, x to the power 5, or x to the power 4, or x to the power 3. And the final term will be y to the power n, y to the power 5, y to the power 4, y to the power 3. With each successive term, exponents of x decrease by 1, as those with y increase by 1. So you can see that pattern is playing out here. The coefficient of any given term, x to the n minus k, y to the k, is n choose k. And again, you can see that playing out here. The triangular array of binomial coefficients, so if we just wrote the coefficients, like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and then we have 1, 5, 10, 10, 5, and 1. So we just wrote these coefficients in a triangle like this. This is called Pascal's triangle. And it's named after a 17th century mathematician. And it has this interesting pattern, which is that each number in the triangle, other than the ones at the end of each row, is the sum of the two numbers to the right and left in the row above. So, for example, 1 plus 1 is 2. 1 plus 2 is 3. Or 3 plus 3 is 6, and so on. You can see these very nice things. Which brings us to the formal binomial theorem. If n is greater than or equal to 0 and x and y are numbers, then x plus y whole to the power n is going to be the sum, k runs from 0 to n, of n choose k times x to the n minus k times y to the k. In order to prove this theorem, we need mathematical induction, which is covered in this textbook, but not in this course on discrete mathematics. So if you are interested in seeing the proof, you can read more about mathematical induction in the textbook. So one thing that we can do with this theorem is to identify a term in an expansion. So for example, if we were asked to find the third term in the expansion of x minus y whole to the power 4, then that would occur when k is equal to 2, because we start at 0, so 0, 1, and then 2 is the third term. So we would have 4 choose 2. The 4 is coming from this power, x to the power 4 minus 2 times y squared, which is 6x squared y squared. Or, rather than just finding a single term in an expansion, we can find an entire expansion, and usually more quickly than doing the distribution by hand. So if we wanted to expand 3x minus 2 whole to the power 3, we can, in the theorem, we can replace x by 3x and y by negative 2. Then the theorem tells us that this expansion should be the sum, k running from 0 to 3, of 3 choose k, 3x whole to the power n minus k, times negative 2 to the power k. And you can see that's 3 choose 0 times 3x cubed times negative 2 to the 0, plus 3 choose 1 times 3x squared times negative 2 to the power 1, and so on. And you get this polynomial, 27x cubed minus 54x squared plus 36x minus 8 when you simplify. So let's do an example of that type. We're asked to expand 2x minus 3y whole to the power 4. So if I replace x by 2x in the theorem, and I replace y by minus 3y, then I can say this expansion should be the sum, k is from 0 to 4 because the power is 4, of 4 choose k times 2x to the power 4 minus k times minus 3y to the power k. So let's write that out. That should be 4 choose 0 times 2x to the power 4 times minus 3y to the power 0 plus 4 choose 1 times 2x to the power 3. I subtracted 1 from 4, and then minus 3y to the power 1 plus 4 choose 2, 2x whole to the power 2 times minus 3y whole to the power 2 plus 4 choose 3, 2x whole to the power 1 minus 3y whole to the power 3 plus 4 choose 4, 2x whole to the power 0 minus 3y whole to the power 4. And then I can find these coefficients. So 4 choose 0 I know is 1. From 2x to the power 4 I'm going to get 2 to the power 4, which is 16. And from negative 3 to the 0 I'm going to get 1. Then I'll have x to the power 4 and y to the power 0. So I'm not going to write it because it's just 1. Then 4 choose 1 is 4. 2 cubed is 8. Minus 3 to the power 1 is minus 3. Then I'll have x cubed y. 4 choose 2 is 6. 2 squared is 4. Minus 3 squared is 9. Then x squared y squared. Plus 4 choose 3 is 4. 2 to the power 1 is 2. Minus 3 to the power 3 is minus 27. Xy cubed. And finally, 4 choose 4 is 1. 2 to the power 0 is 1. And minus 3 to the power 4 is 81. Y to the power 4. So finally, multiplying the coefficients, I have 16x to the power 4. 8 times negative 3 is negative 24 times 4 is minus 96. Minus 96 x cubed y. Then 6 times 4 times 9 is plus 216 x squared y squared. Negative 27 times 2 times 4 is also 216, but it's negative, so minus 216 xy cubed and 81 y to the fourth. So this will be the expansion of 2x minus 3y whole to the power 4. And that was actually much quicker than if I tried to write them all out and do the distribution. I'd end up with so many terms and I'd have to combine like terms. So this is quick and easy. Next, we're asked to find the fourth term in the expansion of x minus 2y whole to the power 6. So in this case, I know that the binomial theorem tells me that x minus 2y whole to the power 6 is the sum, k running from 0 to 6, of 6 choose k times x to the power 6 minus k times minus 2y to the power k. But I don't need to write out the entire expansion, I just need the fourth term. And remember, my k is starting at 0, so the fourth term is actually going to be when k is equal to 3. That should be 6 choose 3 times x to the 6 minus 3 times minus 2y to the 3. 6 choose 3 is 20. And minus 2 cubed is minus 8. Then I have x cubed y cubed. So this is minus 160 x cubed y cubed. So by using binomial theorem, I could quickly find the fourth term in the expansion without having to do the distribution 6 times and end up with so many terms. Okay, explain in words why the following equalities are true based on the number of subsets. So we're going to focus on number of subsets. And then verify the equalities using the formula for binomial coefficients. The first one is, why should it be true that n choose 1 is equal to n? Well, it said, think about subsets. So let's say we have a set and its members are 1, 2, 3, all the way up to n. And I was trying to find all of the subsets that contain only one element. Well, I could have singleton 1, singleton 2, singleton 3, and all of the numbers in between until I got to singleton n. So if I counted how many singleton subsets, there would be exactly n. So if I remember that n choose 1, another way of thinking about that is how many ways can I form a subset of a set with n elements, a subset that has one element? Well, then there are n ways. Now, verifying it using the formula for binomial coefficients, remember that that formula was n choose 1 is equal to n factorial over n minus 1 factorial times 1 factorial. And this ends up being n times n minus 1 times n minus 2, multiplying together all the numbers until I get to 3, 2, 1. And then on the bottom, n minus 1 factorial is n minus 1 times n minus 2, multiplying together all the numbers until I get to 3, 2, 1. And then times 1 factorial, which is times 1. So if I start canceling, then clearly we can see what's left over is n divided by 1, and that's n. Now what about B? B says that n choose k should be equal to n choose n minus k. So if we think about it in terms of subsets, n choose k is how many ways can I pick any k elements to be in a set. So if I've picked k elements to go in my set, then whatever's left over is n minus k elements that are not in my set. So another way of saying it would be how many ways can I choose n minus k elements to not be in my set. Then what's left over is n choose k elements in my set, or k elements in my set, and there are n choose k many ways. So if we wanted to show that using the formula, n choose k is equal to n factorial over n minus k factorial times k factorial. Starting from the other side, if I have n choose n minus k, that should be equal to n factorial over n minus k factorial times n minus k factorial. According to the formula, I just replaced the k in the formula by n minus k. So that is equal to n factorial divided by n minus n is 0 plus k is k factorial times n minus k factorial. So now if we compare these two things, we can clearly see that these are exactly the same, and it makes sense. Next question is, there are 10 points, P1, P2, up to P10 on a plane. No 3 are on the same line. So I have a plane, and there are 10 points where no 3 of them lie on the same line. I might have drawn more than 10 dots, but that's fine. And then the question is, how many lines are determined by the point? So how many ways can I connect 2 dots? Because if I connect 2 dots, then I have a line. So the answer should be 10 choose 2. However many ways I can choose 2 points is the number of ways that I can draw a line. And how many, and let's compute that really quick. That's 10 factorial divided by 8 factorial times 2 factorial, so it ends up being 10 times 9 divided by 2, which is 45. 45 lines I can draw. How many triangles are determined by the points? So that would be, if I choose any 3 points, then I can draw a triangle. Then it makes sense, it should be 10 choose 3, which is 10 factorial over 7 factorial times 3 factorial, which is 10 times 9 times 8 divided by 6, which is 720 over 6, which is 120. Oops, 720. Now, how many ways can n persons be grouped into pairs when n is even? Assume that the order of the pairs matters, but not the order within the pairs. For example, if n is equal to 4, then the 6 different groupings would be, well, I could make a pair 1 and 2, then the leftover pair would be 3 and 4. Or if I made the pair 1 and 3, then the leftover pair would be 2 and 4, and so on. So each of these is a grouping. But what if instead of 4, we had 6? So first I have, not 6, what if instead of 4 we had n? So first I'm going to choose 2 from n, just like I did here. I had chosen 2, and then I'm going to have n minus 2 choose 2, which in this case was 2 choose 2. Then I'll have n minus 4 choose 2 if n is big enough. As in the case of 4, I can't have 0 choose 2. That doesn't make any sense. So I have to stop here at 2 choose 2. And if I calculate this number, this should be 6 times 1, which is 6, and that's exactly what we found. So the number of ways to choose the pairs should be following this pattern: n choose 2, then n minus 2 choose 2, then n minus 4 choose 2, and then eventually we'll get down to 4 choose 2, and 2 choose 2 will be our last choosing. So depending on what n is, will depend how many times we have to repeat this process, but this should give us a general formula. Now, a state's lottery involves choosing 6 different numbers out of a possible 36. How many ways can a person choose 6 numbers? So we have 36 choose 6. And this would be a little unwieldy to calculate by hand, because it would be, well, first 36 factorial, then divided by 30 factorial times 6 factorial. So we'd have 36 times 35 times 34 times 33 times 32 times 31. And the rest would get canceled by the 30 factorial. And then on the bottom, 6 factorial ends up being 720. So that's going to be a huge number. It's 1,947,792. Then the question is, what is the probability of a person winning the lottery with a single bet? So that should be 1 out of 1,947,792, which is very small. There are 5 or 6 zeros after the 0 before you. So the probability is almost 0 of winning the lottery. Now, another interesting thing we could do, a clever way to use the binomial theorem would be to do difficult calculations quickly. So if we wanted to calculate 9,998 to the third power, we could think of it as 10,000 minus 2 and make the calculation much quicker. So 10,000 minus 2 to the third power is going to be the sum. K is from 0 to 3 of 3 choose K of 10,000 to the power 3 minus k times negative 2 to the power k. And that's 320 times 10,000 cubed, negative 2 to the power 0, plus 321 times 10,000 squared, negative 2 to the power 1, plus 322 times 10,000 to the power 1, negative 2 squared, plus 323 10,000 to the power 0, negative 2 to the power 3. 320 is 1, and 10,000 cubed, so I'll have 4 zeros, and then 4 zeros, and then 4 zeros. So whatever that is, negative 2 to the 0 is 1. Plus 3 choose 1 is 3 times negative 2. So negative 6 times 10,000 squared. So that should be minus 6 followed by 8 zeros. And then 3 choose 2 is 3. Negative 2 squared is 4. So we get 12 followed by 4 zeros. And 3 choose 3 is 1. 10,000 to the power 0 is 1. Negative 2 cubed is minus 8. So this ends up being 999, 400, 119, 992. And that would be likely much faster than trying to do 9,998 times 9,998, then getting some gigantic number and again trying to multiply by 9,998. Instead, we can do addition, which is generally easier than multiplication of big, weird numbers. In the card game Blackjack, there are one or more players and a dealer. Initially, each player is dealt 2 cards and the dealer is dealt 1 card down and 1 facing up. The order of the hands, but not the order of the cards in the hands, matters. Starting with a single 52 card deck and 3 players, how many ways can the first 2 cards be dealt? We're going to ignore this thing, although this is related to your interactive textbook if you are using it. So I have a 52 card deck. I'm dealing 2 cards. So this will be first 52 choose 2 to the first player. Then I'm going to multiply that by 50 choose 2. That's how many ways we can deal the next 2 cards to the next player. Then multiply that by 48 choose 2. There are 3 players, but the dealer also gets 2 cards. So we'll multiply that by 46 choose 2. And this ends up being, again, some very large number. Write it here. So billions and billions of ways that the first 2 cards can be dealt at a blackjack table. So we had a couple of questions in this lecture about lottery and poker, blackjack, those things, so you can certainly understand why these games are played, because the chances of winning them is very, very small. That is the final exercise in this lecture note, and this will conclude our module on combinatorics.